Hi there, this is Matt Heffernan. Welcome back to my channel. This is the 18th episode in a series that seeks to demystify programming and assembly language for the 6502 family of 8-bit processors. We're using the Commander X16 as a target, as it has a 65C02 and is a particularly excellent platform for this learning process. If you haven't seen the previous episodes and need to start at the very beginning, please go back to my channel. Don't forget to subscribe and click the bell for notifications while you're there so that you know when the next episodes come out, and start this playlist from the beginning. So far in this series, we have learned the fundamentals of assembly programming by going through the entire 65C02 instruction set and examining how each instruction works, and since then getting into the specific capabilities of the X16. For graphics, we've already seen how the two VERA layers can be used for text, tiles, or bitmaps. But separate from those are the sprites, which are like individual free-floating tiles that the VERA can render using their own unique priority, placing them anywhere in relation to the layers and even each other. They aren't tied to the scroll positions of either layer, but can be placed anywhere on the screen, independent of even the other 127 sprites available for the display. The mouse cursor uses a sprite, but the biggest application of sprites is in games, where you can have characters and animations all doing their own thing, and even define additional graphical layers to add an even greater sense of depth to the look of games. The VERA display adapter supports 128 independent sprites. Each can be between 8x8 and 64x64 pixels in size, and have 16 or 256 colors. Sprites are positioned by their upper left corner, which can be set to any pixel on the 640x480 screen, and in fact even off-screen so that only part of the sprite is visible. The positions are always absolute to the current scale of the display, and not affected by the scroll position of either layer. Sprite assets can be stored anywhere in VRAM, and don't require being in a particular order, like tile assets, but they do need to be aligned to 32-byte boundaries. But because this is a more flexible alignment than tile maps or asset bases, sprite assets can be used to fill in random parts of VRAM where possible. Sprites can be rendered at 3 Z levels, starting with level 1, which is behind both layers. Level 2 is between the layers, and level 3 is in front of both layers. However, the sprites are rendered within these layers on a priority based on their index. The sprites with lower indexes are rendered in front of sprites with higher indexes, and always in front of sprites in lower Z levels. So really, the VERA supports 131 different layers, if you count the solid color background, and all 128 sprite layers can have a configurable priority. In addition to these constraints, there is also a limit to the number of sprites that can be rendered on a single line of the display, depending on the width and color depth of each sprite. The formula is somewhat complex, but generally, you don't want so many sprites on one line that they're all overlapping. Remember, you can always swap out tiles if you need animation without movement relative to the tile map. Sprites also support hardware collision detection with other sprites, but not with tiles. Sprites can indicate up to 4 classes of collision that they support, and visible intersections with other sprites in a common collision class will generate an interrupt, during which the VERA can indicate which of the 4 classes are currently experiencing a collision. To control the general behavior of sprites, we have some familiar VERA registers to deal with, starting with the IEN and ISR interrupt registers. We've already seen how to deal with VSync and line interrupts, but today we are going to get into sprite collision, or SPRCOL IRQs. To enable them, first you need to set bit 2 in the IEN register. Then, when an IRQ happens, you can see what triggered it in the ISR register. If bit 2 is set there, a sprite collision occurred, and this bit is latched just like the others, so it will reset if you write a 1 to it, and then it won't be set again until another collision is detected. The upper 4 bits of the ISR register indicate what kind of collision occurred. As we will see later, each sprite has a 4-bit collision map, and when sprites with the same bit set intersect, it will generate an interrupt with that same bit set in the ISR register. This helps you define different classes of collision. During any IRQ, you can see which collision classes are currently occurring by looking at these bits. But first, to make any sprites visible, you need to set bit 6 in the DC video register, which will enable sprites at all Z levels. Then, to make any sprite appear, it needs to have a non-zero z-level and be located within the currently visible display area. But how do you do this? Unlike the two display layers, VERA sprites are controlled by registers that are mapped to VRAM rather than being directly addressable by the CPU. The Sprite attribute registers start at VRAM address hex 1FC00, and there are 8 contiguous bytes for each sprite, so the last kilobyte of VRAM is dedicated to these registers. The starting address for each sprite can be expressed as 1FC00 plus 8 times the sprite index, which puts the first register for Sprite 127 at hex 1FFF8. The first 2 attribute bytes for each sprite are for the address of the sprite asset in VRAM. But only 12 bits are available for that 17-bit address, which means that the lowest 5 bits of the asset address must be clear, requiring a 32-byte alignment. So if you wanted to place your first sprite asset right after the default text map at hex 04000, you need to shift that address to the right by 5 bits and write hex 200 to the address register. It's little endian, of course, so you'll write 0 to the first byte and 2 to the second byte. However, the second byte also contains another field. Bit 7 is used to indicate the color depth of the sprite. A mode value of 0 indicates 16 colors, and 1 means 256 colors. You can't have 1 BPP or 2 BPP sprites with VERA, but that's just as well, as an 8x8 4 BPP sprite takes up 32 bytes, so anything smaller would just result in wasted space in VRAM. The next 4 bytes contain the x and y coordinates, with x first as a 10-bit little endian value. The x coordinate can range from 0 to 639, and the sprite will be visible on a full-scale display. You can even give the x coordinate a value less than 0 by putting a negative 16-bit value in those 2 bytes, even though the upper 6 bits will be ignored. This means that all 10 bits set will be interpreted as -1, and the sprite will have its rightmost column of pixels off screen. So the range is effectively -63 to 639, and anything outside that range means the sprite will be completely off screen. -64, represented as a signed 10-bit value, is the same as 960 unsigned, so the invisible range could also be interpreted as 640 to 959. The same sort of math applies to the y-coordinate in the 2 bytes after x, but the range is further constrained, with the highest positive value being 479 with a full-scale display. Of course, if you've set your display scale to be less than full scale, only the sprites in the visible upper left corner of the logical 640 by 480 display will also be visible. The pixel coordinates of your sprite position will always scale along with your display. After the coordinates is a byte containing the collision mask, z-depth, and flipping indicators for the sprite. Each sprite can have any of the 4 collision mask bits set in the upper nibble, and intersecting with any other sprites with the same bits will trigger a collision interrupt. Bits 3 and 2 hold the z level, with a value of 0 effectively disabling the sprite. A value of 1, 2, or 3 will place the sprite in the priority order we saw earlier. Setting bit 1 will flip the sprite vertically, with each row of the sprite asset rendered in reverse order. Bit 0 is for flipping horizontally, and it can be combined with vertical flipping to have an asset get rendered in 4 different orientations. The 8th and last attribute register byte for each sprite sets its dimensions and palette offset. Bits 7 and 6 set the height to 8, 16, 32, or 64, based on a value of 0, 1, 2, or 3, respectively. The same value mappings apply to bits 5 and 4 to set the sprite width, so that you can have any combination of the 4 dimension values. Like I said earlier, the minimum size of a sprite is 32 bytes, which would be for an 8x8 Mode 0 sprite. The maximum size is a whopping 4 kilobytes for a 64 by 64 Mode 1 sprite. So maybe not every combination is a great idea, but you do have a lot of flexibility in between. The lower nibble of this last byte indicates the palette offset for Mode 0 sprites, and this works just the same as palette offsets for tiles and bitmaps, by mapping color index 0 to 16 times this offset. Also, like other assets, sprite pixels using color index 0 will be transparent, and not cause any collisions either. Only opaque pixels with non-zero color indexes will be rendered and cause collisions when intersecting with visible pixels from other sprites. Sprite assets can be stored anywhere in VRAM and are formatted just like individual tiles, without the need of being the same dimensions of other assets, or even stored alongside others. Mode 0 sprites use 4 bits per pixel for 16 color depth, and can be configured to use any 16 color palette offset. The starting address of an asset must be at a 32 byte boundary, but Sprite assets are always going to be even multiples of 32 bytes, so even differently sized sprites can be stored contiguously to have larger contiguous areas of VRAM for tiles and bitmaps. Just like in tiles, Sprite pixels with color index 0 are always transparent, regardless of the palette offset. You can make your sprites look more diverse with the trick of just changing the palette offset, which was done quite often in classic games like Pac-Man and Super Mario Bros. Mode 1 sprites take up a full byte per pixel, meaning twice as much VRAM than Mode 0 sprites of the same size. These sprites can use any color in the full 256 color palette, with color index 0 still being transparent. You could try going Neo Geo with a bunch of giant Mode 1 sprites all over the screen, but you'll run into some serious constraints when it comes to the VRAM needed to store the current visible assets, the limited number of 8 BPP sprite pixels per line, and the time required to transfer asset data from CPU RAM to VRAM, as you won't be able to fit many animation frames in VRAM at once. So you need to be judicious in how many Mode 0 sprites you use, where you intend to put them, and how detailed you want their animation to be. You will find that the X16 can keep up with consoles of the 16-bit era, like Super Nintendo, but without the ability to do things like Mode 7 rotation or FX chip polygons. Also, the absence of DMA loading into VRAM means that you want to keep all the assets you need quickly in VRAM, even when they're not being rendered. Now let's go through a case study where we define a sprite asset in RAM alongside a program that will copy it to VRAM and then configure the attributes for Sprite 1 to use that asset and place it 150 pixels from the left side of the screen and 100 pixels from the top. We're going to use palette offset 1, which is a grayscale palette, which we can use to make a simple 8x8 pixel silver ball, just like you can see here. First, we need to define some constants for the VERA registers, and then VRAM addresses for first the ball sprite asset, and then the start of the attribute registers for Sprite 1, which is 8 bytes past the beginning of the sprite attributes at hex 1FC00. Then in RAM, we define the 32 bytes we need for the silver ball, which we label AG ball, and then specify 4 bytes per line, which will also define a row of pixels. As this is a Mode 0 sprite, the asset is 4 bits per pixel, so each nibble of asset data is a color index. Zeros are transparent, of course, and with palette offset 1, the color indexes get brighter until you go all the way to white at hex F. So 8 lines of 4 bytes each will line up exactly with 8 rows of 8 pixels each. Now we can copy this data to anywhere in VRAM, as long as it has a 32-byte alignment, which your constant VRAM ball does, which you can easily tell because it has 0 in its lowest nibble, and the next nibble up from that is even. Then we start our subroutine, which we label placeball. The red code at the beginning sets up VERA data port 0 to point to the VRAM ball address with a stride of 1, because we want to copy all 32 bytes contiguously. So we go right into the blue code where we initialize x to 0, then enter a loop where we index into AG ball with x, and copy that byte to VRAM, then increment and keep looping until x hits 32, and then we have the whole asset in VRAM. We then continue on to the gold code, where we now set up VERA data port 0 to point to the beginning of the Sprite 1 attribute registers in VRAM, using the constant we defined and a stride of 1 again, as we need to set all 8 registers. In the green code, we go on to set the values we need in each of them, starting with the address of the asset, which we need to shift 5 bits to the right, then put the low byte into the first register and the high byte into the second, leaving bit 7 clear to indicate that this will be a Mode 0 sprite and this asset will be 4 BPP. Then we set the x-coordinate to 150, which is less than 256, so it will fit in a single byte, and we can just zero out the high byte of the x-coordinate. Then we set the y-coordinate to 100, which also needs the high byte zeroed out. Then we place the sprite at Z level 3 by writing hex 0C to the next byte, which also leaves the collision mask clear as well as both of the flip bits, which means the asset will be rendered in its normal orientation. Finally, we set the last byte to 1 to specify palette offset 1, which will give us the desired grayscale, and leave the upper nibble clear, which specifies dimensions of 8x8 pixels. Then the sprite should be visible in the next video frame, but for now we can just return, and that sprite will continue to stay there until the attributes are modified again. Before we get to our example, let's take a closer look at how sprite collision works. We already saw how the IEN and ISR registers handle interrupts, and how the collision mask can be set for each sprite and its attributes. But just to clarify, when the sprite collision bit is set in the IEN register, any time two sprites intersect, their collision masks are ANDed together, and that goes into the collision mask in the ISR register. Then the sprite collision bit is also set in the ISR register if any of the collision bits were set and the IRQ is triggered. So in the IRQ handler, we have some insight into which type of collision has occurred based on the collision mask in ISR. And we don't necessarily have to figure out exactly which sprites intersected, and we are also saved the need to write the collision detection in our own code. The VERA will automatically consider any opaque bits overlapping to be a collision, and will set up the ISR register accordingly. To illustrate this, we will define 3 sprites, each with their own unique collision mask. Our player avatar, Mario, has a mask of binary 0011. This means it can collide with sprites in both classes 0 and 1. The coin sprite has a mask of 1010, which means it can collide with classes 3 and 1. And finally, the little Goomba has a mask of 0101, so it collides with classes 2 and 0. Now when Mario intersects with the coin, it triggers a collision with binary 0010, because this was a class 1 collision, which we could then interpret as an avatar item collision. If Mario collides with the Goomba, it is a class 0 collision, which we can then call an avatar enemy collision. We could then come up with different kinds of collisions for classes 2 and 3, or combinations of different classes where the sprites have more than one collision mask bit in common. One last thing we need to address is the mouse cursor, which we touched on earlier in the episode on the mouse and joystick interfaces. Sprite 0 is reserved for the mouse cursor whenever the mouse is enabled, so then you really only have 127 sprites to work with in that case. But if you call the mouse config kernel subroutine with 0 in the accumulator, it will disable the mouse, and then you can use Sprite 0 however you like, but take caution. There's always a good chance that the mouse could be enabled again, and then the kernel will take over that sprite and you can no longer control its position, and you can get a lot done with the other 127 sprites, so it's best practice to stick to those. If you set A to 1 before calling mouse config, it will use the default mouse cursor, which you don't have to load into VRAM. It's just built in, and makes a perfectly good general-purpose cursor, as you can see here. But if you set A to hex FF when you call mouse config, you will need to configure the Sprite 0 attributes yourself. You still can't change the position, but you will need to point to an asset in VRAM, and make sure your attributes will support it. If you don't have the attributes set properly, the mouse cursor could be just a floating blob of garbage, and that's not a great user experience. Now we're going to get into our example program, which will combine a custom mouse cursor with a programmatically controlled sprite. Our mouse cursor will be a spinning ball, and it will continually cycle through an animation sequence. The other sprite will be positioned based on the mouse cursor position, but reflected through the center point of the screen. This shadow sprite will use the same assets for its frame sequence, but using the grayscale palette offset 1 to make the mouse cursor more colorful, as that uses palette offset 0 for the default 16 colors. Then when the mouse cursor approaches the center, it can intersect with the shadow sprite, which we can use to trigger a collision that will make a beep play as long as the collision is still happening, then shut off when they separate again. So let's get right into the code. We start with a standard segment preamble and jumpstart, then we include x16.inc, which gives us all the register addresses and a bunch of other general stuff we'll need, as we saw in the previous video in this series. We'll still need a few constants, starting with 0-page locations to store the mouse coordinates, then some bits we need to deal with the VERA registers. We have the bits for VSync and sprite collisions in the IEN and ISR registers. The collision mask we're going to check for in ISR and put into our sprite attributes, and then the bits we are going to set in the DC video register to enable sprites and layer 1 text and use VGA output. Then we have the bits we need to set in the sprite attributes, so we can specify Z level 3, vertical flipping, horizontal flipping, and dimensions of 32 pixels high and wide. We're going to need some VRAM addresses too, including the start of our sprite frame assets, the attributes of our shadow sprite, and the attributes for a third sprite that we'll talk about soon, which we'll call the sync sprite. We need some constants to deal with the size of the assets, which are going to be 32 by 32 pixels, but 4 BPP, so we can divide by 2 to get the actual number of bytes for each 32 by 32 frame. Our little animation will have 20 frames that can loop seamlessly, and we can use that to calculate the ending VRAM address of the sprite assets. One last constant will be for the Petsky character Q, which we'll use to quit the program. For data, we'll need a word to back up the default IRQ vector, then another for the current frame VRAM address, which will be formatted to be quickly written to sprite attributes. Since these assets will take up a considerable amount of memory, we just want to load them directly into VRAM. So we need to first allocate a string in RAM for the file name of a bitmap containing 32 by 640 pixels, which will have every sprite frame laid out in one big column, which is how they'll need to be stored in VRAM. We also throw in another label that we can use for calculating the length of the string by putting it right after the last character. We start our code by initializing the global frame variable to the first sprite frame asset address, using the VRAM sprite frames constant we defined, and shifting it 5 bits to the right to match the format of the sprite attributes registers. Then we load all the frame assets directly to VRAM, first specifying the SD card file system, then the sprites file name we defined in RAM, and then loading to the VRAM sprite frames address, adding 2 to the bank number to specify the destination as VRAM instead of regular CPU RAM. We want to use a custom mouse cursor, so we call mouseconfig with hex FF in A and 1 in X, as this program will use the full-scale 640 by 480 display. Then we want to configure the sprite attributes to use the assets we loaded, starting with the mouse cursor, which uses sprite 0. So we set up data port 0 to point to the beginning of the sprite attribute registers in VRAM, using the VERA set address macro and the VRAM sprite attribute address constant, both defined in x16.inc. We write the initial value in frame to the first 2 bytes, leaving the high bit in the second byte clear to specify mode 0. We leave the position, collision, Z level, and flipping bits alone, as we won't be able to control them anyway. Then we specify a 32 by 32 sprite using palette offset 0 in the 8th and last byte. Data port 0 is now pointing to the attribute registers for sprite 1, which we'll use to control the shadow sprite. We use the same frame address here, and then leave the position alone, as we will be basing that on the mouse position later. We set the collision mask value we defined earlier, Z level 3, and flip the sprite both horizontally and vertically. Finally, we set sprite 1 to be 32 by 32, but this time with palette offset 1, so it will be grayscale. We have one more sprite to set up, which we are going to call the sync sprite. Since we can't set a collision mask for the mouse cursor, at least at the time of this recording, sprite 2 will just be placed directly under the mouse cursor, updating its position as the mouse is moved, so that it always stays hidden, being a higher sprite index, but we'll have a collision mask so that we know when the mouse cursor is intersecting with the shadow sprite. We initialize it to the first frame as well, but as each frame is the same circular shape, we'll never have to change this one. We can leave the position alone here as well, but we set the collision mask and make it Z level 3 with no flipping. Finally, we set the last sprite attribute byte to make the sync sprite 32 by 32 as well, and we'll just leave the palette offset as 0, but it doesn't really matter as it will never be visible. We want to initialize the programmable sound generator, or PSG, to have channel 0 set to approximately 1000 Hz, which is hex 0A7C in the PSG register format. Like the sprite attributes, the PSG registers are also mapped to VRAM, so we use the VERA set address macro again and pass in the beginning VRAM address of the PSG registers, which is also defined in x16.inc. We load up the frequency registers with OA7C as little endian, Then zero out the third byte to make sure the channel is off right now. And finally set the fourth and last byte to hex 40, which will give us a sawtooth wave, which makes a nice sharp beeping sound at 1000 Hz. Then we do the usual backing up the default IRQ vector and replace it with our own custom IRQ handler, but this time enabling sprite collision interrupts. Then we get to our main loop, which simply waits for an interrupt in low power mode, then checks the keyboard buffer after the interrupt returns. If anything other than a Petsky Q character shows up, we keep looping. Once we get that cue, we restore the default IRQ handler, disable the mouse, and clear the other two sprites manually. We do this by specifying the 7th attribute register byte of each sprite by adding 6 to the base address, and passing that to the VERA set address macro. You'll notice this time in each instantiation we pass a 0 for the second argument, which means we don't need a stride, as we will only be modifying a single byte at that address. Zeroing out these bytes sets their Z levels to 0, which makes them disappear. They'll still have the same position if we gave it a non-zero Z level later, but for now they'll be out of the way. Then we shut off the sound and return to BASIC, and our program is done. But we still need to define our custom IRQ handler, where all the sprite effects are going to happen immediately after each VSync, which should prevent tearing. So first we check to see if the VSync bit is set in the ISR register, and if it is, we branch ahead to @nextFrame. Otherwise, we jump ahead to @continue because this isn't a VSync, so we just want to go right to the default IRQ handler. If this was a VSync, then we end up branching to @nextFrame, where we want to advance the frame variable to point to the next frame in VRAM, still using the format where the address is shifted 5 bits to the right. We use the sprite size constant we calculated earlier and add that to the frame. Then we check to see if the new value of frame matches the nSprites constant that we also calculated earlier. We check the high byte first, as that was already an A after the previous addition. If the high bytes don't match, we branch ahead to @setFrame. Otherwise, we check the low bytes and branch to @setFrame if those don't match either. But if both bytes match, we reset frame to the starting address at VRAM sprite frames. We then fall to @setFrame, with the new frame address loaded in the frame variable. We set up data port 0 to point to the beginning of the sprite attributes, where we can write the frame address to the sprite 0 address registers. Then we skip ahead to the shadow sprite by resetting the VERA address to the start of the shadow sprite attributes, and write the same frame address there. But we're not done, as we want to also update the shadow sprite position. We call mouseGet with the 0 page address we reserved for the mouse coordinates in X. Then we subtract the mouse X coordinate from 608, which will reflect it across the center, and store the difference in the X coordinate for the shadow sprite. We then subtract the mouse Y coordinate from 448, which will reflect across the middle, and store the difference in the shadow sprite Y coordinate. For the sync sprite, we only want to update the position to match the mouse cursor, so we reset the VERA address to the third byte of the sync sprite registers, where we simply copy the mouse coordinates to the sync sprite coordinates. With all the sprites now in their new positions with their current frames, we are ready to check for collisions. What we will see in each VSync is actually the collision state for the previous frame, but at 60 Hz it won't make a real difference. To prepare, we reset the VERA address one more time to the third byte of the PSG channel 0 registers by adding 2 to the starting address of the PSG registers in VRAM. Then we check to see if the collision mask we specified is in the ISR register. If it isn't, we branch ahead to @clear. Otherwise, the collision happened on the last frame, so we maximize the PSG volume by writing hex FF and unconditionally branch to @continue. If the collision didn't happen, we store a 0 to the volume register, which will turn off the sound if it was playing already. Finally, we fall to @continue, where we reset the sprite collision and VSync latches, even though we aren't actually checking the sprite collision bit, but it's good practice anyway. Then we jump to the default IRQ handler, and we're done. Of course, there's a build script. Before we build the assembly code, we convert the raw sprite bitmap to the format we need to load into VRAM, which we do by calling the included Python script for bppsprites.py. This is a simplified version of the script we created in a bitmap example a few episodes ago, and you can check out that video if you want to see how that works. With sprites.bin built, we then build sprites.prg from the code, and we're ready to run. Let's go try it in the terminal. Let's run build.sh. And we'll check our directory listing to make sure that we have our Sprite assets and program, and we're ready to go. So let's run that emulator, and we'll maximize it to see our fancy balls. Let's load sprites.prg and run it. There we see the mouse cursor, which is a red ball, and the shadow ball in gray. As we roll the cursor around, we see the rotation animation happening on both sprites, and the shadow sprite acting like a reflection through the center point of the display. If we move the cursor closer to the center, it eventually hits the shadow sprite. And we hear our beep. We pull it away, and the beep stops. So that's it. Not too useful or fun, but a good illustration of how to manage sprites. Let's hit Q, and we're back to basic. We have now learned about all the different ways of creating graphics, but there's still more to come, and soon you'll be able to command every part of the X16. If you don't want to miss any episodes in the future, make sure you subscribe to my channel and click the bell to get notified when they come out. If this episode taught you anything, please click the like button. And if you have any questions, please put them in the comments, and that can influence how future episodes are made. If you can't wait for the videos to go public, become a patron and get access to new videos as soon as possible, just like the folks you see here did on my Patreon page, which you will find linked in the description, along with the GitHub repo containing all the materials for this tutorial series. Thanks for watching, and I hope to see you again soon. Bye-bye.